Okay, hello everybody and welcome back. Chris Pliley here once again talking to you about Map 235, continuing to talk about standard deviation. And today what I really want to talk about is why we have a different formula for the standard deviation of a sample and of a population. So we already did one example of finding standard deviation using the population formula, and I want to tell you why, if I'm specifically referring to a sample, we should use a different formula. So the bottom line is this, that when I am doing statistics and when I am sampling, what I'm doing is I'm taking some subset of the population, but I'm trying to use that information to infer something about this larger population. So for example, let's suppose that I took a sample of 50 students at UVI, and I went ahead and took their average age, and I said their average age was something like, 23.4 or something like that. Then what I'm really hoping is that this, as I try to put a decimal in there it goes. What I'm really hoping is that this number, 23.4, is somehow indicative of what the average age of all students at UVI really is. And so if I went ahead and took the standard deviation of my sample, and let's say I found it to be, 3.1 or something to that effect, then I would hope to use this number also to somehow infer things about not 50 students, but about all the students at UVI. I don't have access to all of their information, but I'm still trying to say things about that larger population. So I want my sample statistics to be sort of as close as possible to what that real, true, unknown statistic really is. And so, what's the problem? Why can't I just go ahead and use the same old formula? There's no new formula for the mean if I switch from a sample to a population, so why should standard deviation be any different? And well, let's illustrate this with an example. So what I have here is, once again, our favorite histogram, the Best Actress winners, and keep in mind that this represents what we'll call a population. This is the data for all 87 actresses who have ever won the Best Actress award. So this is the entire population. And just so we know, so we have it in the back of our head, I went ahead and found the standard deviation for all 87 actresses. I used Excel. I could have done it by hand, but you can also use software like Excel, like I make you do in homework number 2, so make sure you practice. But the standard deviation of this data set is 11.4 years. So, let me ask you a question. What do you think would happen if instead of having all 87 actresses at my disposal, I only had, let's say, a subset of 20 actresses or something to that effect? Instead of having all 87, I only had 20, and I went ahead and took their standard deviation. Well, it wouldn't be exactly 11.4. That would just be a coincidence. But what do you think? Do you think it would generally be higher or lower than 11.4? Well, I don't know. What do you think? Let's take a look at what actually happened. So here are some random samples. It says 10 here, but it's really 20. Here are some random samples of 20 actresses and the standard deviations of those 20 actress ages. So what I did is I took my list of 87 actresses in Excel. I used a random number generator to select 20 of them, and I took those 20 ages, 22.5, well, there was no 0.5s, let's say it was 22, 34, whatever. I took this big list of 20 ages, and I found its standard deviation. And I found these numbers down here, 10.2, 10.8, etc., represented the standard deviations when I used the population formula. And so what do you notice about these ages? Do they seem to be, in particular in comparison to our standard deviation of 11.4, do they seem to be larger or smaller in general than 11.4? They seem to be smaller, don't they? In fact, I only ended up with 2 out of 10 of these numbers that actually happened to exceed 11.4. It seems that the population standard deviation formula is spitting out numbers that, by and large, tend to be less than the true standard deviation. And if I go ahead and take the mean of those numbers, it happens to be 10.5, which is much less than the actual standard deviation of 11.4. 4. And so what's happening is that the formula for population standard deviation has an inherent bias in it. It's what we call a biased estimator. And that means that by and large, if I do this, if I could pick all the possible subsets of any given size of my population, and I find all of the standard deviations of all of these thousands and thousands of subsets, then the standard deviations would always be coming out with an average which is below the true standard deviation. So in all likelihood, if you use the population standard deviation formula, which is right here, when you are dealing with a sample, the number that you get is likely to be too small, in the sense that it's likely to be less than the true standard deviation. So this can be a problem. So how do we adjust for that? How do we fix the formula so that it gets just big enough that it's no longer biased? Well, it turns out to be that there's quite an easy fix for this. And in the population standard deviation formula, when I do my averaging step, remember I take all my data points, I subtract the mean, I square it, and then I average them. Well, we don't take an average in the traditional sense when we have a sample. We sum up all of our values, and instead of dividing by the full population size, instead of dividing by n, we just divide by n minus 1. And why would we do that? Because, well, that's going to make this number a little bit bigger, right? If I have any kind of fraction, and I divide by a smaller number, what's the bigger number, 5 over 2 or 5 over 3? If I divide by a smaller number, my number just gets a little bit bigger, right? And so dividing by the smaller number, n minus 1, as opposed to n, makes this just a little bit bigger than our population standard deviation. And look what happens. This is the same samples of 20 actresses, and instead of using the population standard deviation formula, I used the sample standard deviation formula. And see how my numbers got a little bit larger? 10.7, 11.5, 10.0, and so on and so on. And I compare this to what I had before. See how much closer they are as a whole to 11.4, which is what I really want. I really want to use these numbers to estimate my real population. Of course, it's not perfect. And notice, of course, none of them are actually equal to 11.4. When I do actually take a sample, I don't expect my data to be exactly representative of my population. This is the error that we experience in statistics. But they are much closer. And if I take the mean of these numbers, it's 11.1. Just dividing by 1 less. Notice what I did. I divided, instead of dividing by 87 in that, instead of dividing by 20 in my averaging step, got careless there for a minute, I divided by 19, and it's a seemingly innocuous small calculation, but look at the difference that it made. It brought my standard deviations as a whole much, much closer to that magic number of 11.4, which is what I'm trying to use these numbers as estimates for. If I randomly picked one of these numbers, there's a higher likelihood that it's close to 11.4 than if I randomly picked one of these numbers, and that's the whole point. And so, the bottom line, the conclusion is that if you know that you are only interested in the data that you have, if you're not trying to make any conclusions about something greater, if you have a class of 25 students and you only care about them and you have all of their information, if you're only concerned with a certain small or a set of people of which you have all of the data, then this is a formula that you should use. If you're dealing with a population, then you use this standard deviation formula. However, if you intend to draw conclusions about some larger group, if what you have is a sample, and this is why it's so important, in Chapter 1 we learn how to distinguish between a sample and a population. The first question you ask yourself is this a sample, is this a population? And if you know you are dealing with a sample, then to get a better estimate of the population standard deviation, you have to use this formula. The only difference is that you divide by n minus 1 rather than n. These are the same, these are just the mean, this is just a symbol, doesn't mean anything. The difference is just in dividing by n minus 1, the sample size minus 1, as opposed to dividing by n. That's it for today. I'll see you next time.